Hello friends, I welcome you to Letstute. Let us just wait. I wanted to see. Okay, welcome Swarna Pramila, Anju Basnet. Okay, let's wait for one more minute. Okay, fine. Then let us start. Let me introduce myself. I'm Keshava Internika, and I welcome you to Letstute. And hi, Vami Reddy. I've done a master's in engineering mathematics, and I'm teaching mathematics since 11 years now. So today, let us try to understand what are real numbers. Hello, Vignesh. So today we are going to start with real numbers. Let's see how many are joining. Let me wait for 30 seconds more. Then we'll start with the concepts. Meanwhile, let us discuss that you have already gone through a few of the aspects from real numbers in some of the some parts of your syllabus maybe. So I'll just try to introduce a few more things, what all things you can understand and what all things we need for further concepts. We'll try to look into all those things. Fine. So let me just start with a number line. Okay. So on number line, we all know that, the middlemost value is 0. Okay. And on the right hand side, we have positive numbers. Let me just, the numbers 1, 2, 3, 4, etc. Dot, dot, dot. Similarly, on the left hand side, we have negative numbers, -1, -2, -3, -4, etc. Now, generally we write these numbers, but we don't write decimal numbers or fractional numbers on the number line because it is easier to understand, it is easier to write. But why do we do that? Because these are the numbers which we are familiar with. Okay, so if I start with 1, 2, 3, 4, and etc., these are the numbers which we use to count objects, count anything. Correct? We start with 1. So they are actually existing naturally. It comes naturally. So they are called as natural numbers. Natural numbers. Okay. And in mathematics, they are also denoted by capital N. Sometimes they put these double lines to just to write it in that way, in that text. So they are natural numbers, and they are also called as positive integers because these numbers, non-decimal numbers or non-decimal numbers, I should say, we don't have any digits after the decimals. Basically, if it is 4, we can also write this as 4.0. 0 indicates that we don't have any other number after decimal, correct? So but if we have if we don't have such things, then it is called as like in the case of 4, we don't have any digit after decimal, correct? This is natural number. Similarly, we have some numbers on the left hand side of the origin, I mean the left hand side of the 0. Even they are actually looking like these numbers, only the difference is they have negative sign with them, they are carrying negative sign. So basically, when these numbers are written together, they are called as integers. Let me write over here, they are called as everything together. Okay, they are called as integers. If I want to make an hierarchy, let me make an hierarchy here. First comes is integers. You have two branches, positive integers and negative integers. That's what we are seeing on the number line, right? On the right hand side of the 0, we have positive integers. On the left hand side of the 0, we have negative integers. And what about the numbers in the right hand side? We have some sections over here as well. from positives, we have odd, even, correct? We have odd numbers and even numbers. We have here as well, right? Odd and even. Fine. And what else we can understand from here? Apart from integers, uh, we got natural numbers. And next thing which we need to understand is whole numbers. Whole numbers. What are whole numbers? Whole numbers are basically the natural numbers, but along with zero. If I also take 0, this is union. I'm actually adding this number to natural numbers. So that means I have to start from 0. So 0 onwards, if you start counting the numbers, those numbers are called as whole numbers. So basically, these are starting from 0. So we can say that 0, 1, 2, 3, etc. They are called as whole numbers. And natural numbers are 1, 2, 3, 4, dot, dot, dot. So continue. So in that way, we get two categories of numbers. One is natural number, second is whole numbers. And then let's go to rational numbers. Rational numbers. Okay. What I want to explain you here is a very simple trick to understand rational numbers. Okay. Rational numbers, if you see, we have a word ratio in the name itself. Ratio suggests that any number in this form where a and b are integers, right? A should be integer as well as b should be an integer. If we take ratio of any two integers, they are called as rational numbers. Let us try to understand where they are located on the number line. Suppose if I want to take a number between 0 and 1, suppose this is the number, I'm taking it as 0.5. That 0.5 can also be written as 1 by 2. Correct? So if you see, if you notice over here, 1 is an integer, 2 is also an integer. So it is a ratio of two integers. Therefore, 0.5 is called as a rational number. Rational number. Okay. So let's go down a bit. Let's go down a bit. Mhm. So it's becoming interesting. Let me draw the number line again. Fine. So I was talking about the rational numbers. I took a number between 0 and 1, that is 0.5, and I told you that 0.5 can also be written as 1 by 2, where 1 is an integer, 2 is an integer. Therefore, it is a fraction of or ratio of two integers. Therefore, it is called as a rational number. But what about the integers? Aren't they rational numbers? Let us check. If I'm talking about 2, what happens to this? This 2 can be written as 2 by 1, correct? Yes, we can write. So what about this 2? 2 is an integer? Yes, it is an integer. It is an integer. What about this 1? Even this is an integer. Okay. So what was the definition? What we have decided that whenever we take ratio of two integers, it is called rational number. So in that case, this 2 also becomes a rational number. Rational number. So in that case, all integers will be rational numbers? Yes, of course. All integers will be rational numbers. Will be rational numbers, correct? So now we started with only the counting numbers, which we called them as a natural number. Then we started with 0 and we call them whole numbers. Let me write the list over here. We should not miss them. We started with natural numbers, which starting from 1, and then we have talked about whole numbers. Whole numbers starts from 0 and onwards, and then we are talking about rational numbers. Rational numbers are basically the ratio of two integers. Okay, so uh, in that case, even the natural numbers are rational numbers, because every natural number can be written as a fraction where denominator is 1. Like if I want to write 1000, it is an integer, but I can also write it as 1000 divided by 1. So therefore, this is a fraction, a ratio of two integers. So even this is a rational number. So basically, rational number involves or includes all the integers along with some more numbers which are represented by decimals, like this one, 0.5. Correct? It is a rational number. If I want to take if I want to take 1.5, 1.5, let me write over here, 1.5, I can write this as 3 by 2, where 3 is an integer and 2 is an integer. So from this we understand that in rational numbers there are more numbers than integers. Correct? Because integers are anyways involved in rational numbers, but along with that we have some other numbers which are represented in decimal form. They are also considered under rational numbers. But is it that all the decimal numbers are considered for rational numbers? No, that's not true. That's not true. Because we have numbers like uh, pi. Pi is decimals. Its value is in decimals, like 3.14. It goes on. It never ends. It never ends. But the question is, can we represent these numbers in the form of ratio of two numbers? I'm writing a by q, or to make it more general, like how we write. Let me keep it not as a by q. Let me make it a by b, maybe. Okay, a by b. So is there any is there any case where a and b both are integers? Absolutely not. You will not get any two integers to whom on dividing whom in this way, in this fashion, we should get pi. We are not going to get those numbers. So in such cases there is a difficulty, right? We cannot involve this in rational numbers, because there is a strict rule for rational numbers that each and every rational number should be able to represented by this form, a by b. But uh, in this case, in case of pi, we are not able to do that. So therefore we can say that it is not a rational number, because uh, uh, see, because uh, it is not a rational number, then what should we call it? Yes, there is a name. It is called as irrational number. Irrational numbers. Okay. So what do you understand from irrational numbers? They are the numbers which cannot be represented as fraction of any two integers. Correct? There are many such examples, like root 2 is 1.414, goes on. It never ends. It never ends. Root 3, it is 1.732. It never ends. It goes on. So these numbers are basically irrational numbers, because you can never write, or we cannot represent them in the form of fraction of two integers. Yes, there are few numbers like 0.6667. I mean, I should not write 7, because I'm trying to tell you the repetitive numbers. Suppose if I want to write 0.666, this is never ending. Suppose this is not, it's not ending, it's going on. But is there any way of writing this in the fraction of two integers? Yes, there is a way to write this. How can we write this? Just to make sure you know this, let me just make it very clear. We can divide by like there are few more numbers, like if suppose if I want to divide 6 by, suppose 5 by 3, I want to divide 5 by 3, not 3. Let me take some other example. Suppose if I want to divide 5 by 3, what I'll get? I'll just divide and show you. It becomes 3 ones are 3, 2 is remaining, so we put 0. So we take 3 6 are 18, again 2 is remaining, we put 0 because of decimal. We get 3 6 are 18, again 2 is remaining, we for decimal we take 0. So it goes on, the story goes on, it never ends. Correct, it never ends. Similarly for this, you know, we can take something else, some other fraction. So in this way, it is not ending, but still we can write this in the form of fraction of two integers. Correct. Let me take one more example. Let me remove this from here. Let me take one more example. Suppose if I want to take 7 by 3. Okay, so what this will be, 3 2s are 6, 1 is remaining, so I'm taking decimal over here, so it will be 10. So 3 3s are 9, so again 1 is remaining, so due to decimal we take 0, so it becomes 10. So 3 3s are 10. So in this way you will keep on getting 3. So in this case also it is never ending, it's going on. We will get continuously this digit 3, but still we are able to write this in the form of fraction of two integers. So what do we understand? That only the never ending decimals will not conclude that it is irrational number. Okay, so from this what we understand is irrational numbers are basically never ending, never ending, as well as never repeating, never repeating. Only in this case the numbers will be called as irrational numbers. Okay, I repeat, if you see in this case, the numbers will never repeat like this. See, in this one we have a pattern of repetition, right? It is repeating. Even in this case it is repeating. So when the numbers are never ending, only that condition never concludes that it is an irrational number. It has to be non-repeating also. It is not ending and it is not repeating. So therefore they are called as irrational numbers. Even in this case, it is not repeating and it is not ending. So even this case we call it as irrational number. Even in this case it is never repeating or never ending. So therefore even pi is irrational numbers. Okay, in case of this 2.333, even though it is never ending but it is repeating, so therefore it is not irrational number, it comes under rational number. Even in this case the numbers are never ending but they are repeating, therefore this is called as rational number. So hope you understood. We started with natural numbers which occur naturally. Okay, we can say that they are generally, people call it as the numbers which are existing naturally. It is not, nothing is added, nothing is removed from these numbers, they are existing naturally, therefore they are called as natural numbers. And the whole numbers, when we add, or we can, if we include 0 in natural numbers, we get whole numbers. And then uh, we understood that combining natural numbers and whole numbers we get integers. Okay, the combination of natural numbers, whole numbers, as well as negative integers. So I was writing a hierarchy. Hierarchy was like something, this integers, and from integers we get negative integers, and we get positive integers. Okay, and positive integers are also called as natural numbers. Natural numbers. Okay, and then we get rational numbers. Rational numbers. Rational numbers are basically a ratio of two integers, right? Suppose if I want to write a by b, a is an integer, b is also an integer. And if I want to write irrational number, let me write here irrational number. Irrational numbers are non-repeating, and never ending, never ending. Okay, so we saw three categories, right? Rational, integers, irrational. So combining everything, we get the topic of this video is real number. Real numbers. So real numbers, all the integers are real numbers, all the rational numbers are real numbers, or irrational numbers are real numbers. So basically, real numbers is the combination of all types of numbers. Okay, so real number is the superset, where rational numbers are subset of real numbers, integers are subsets of real numbers, irrational numbers are subsets of real numbers. Okay, so now hope you have idea about what is integers, what is natural number, what are whole numbers, what are rational numbers, what are what are irrational numbers. So these things are important for understanding the chapter further. Fine. So now you have the idea about these things. Now next thing what we are going to study is Euclid's lemma. Euclid's lemma. Okay, what is Euclid's lemma? Lemma is basically any statement which is proved, which is already proved. You don't have to prove this again. That is called as lemma. So Euclid's lemma. What is Euclid's lemma is stating? I'll just let me give you the definition, or I can say that, let me explain you this. Suppose A and B are, A and B are positive integers, and uh, suppose if I want to show it as, say, A and B are positive integers. Suppose if I can show this as A equals to BQ plus R, where Q and R unique, where R is less than greater than equal to 0 and less than B. So this is what Euclid's lemma suggests, that whenever you have two positive integers A and B, you have two more integers and they are unique, and therefore you can represent A or one of the integers as this way. Okay, like for example, let me take an example, 4 and 2. Okay, if I'm taking A as 4 and B as 2, I want to figure out what is Q and what is R. Okay, so in this case I'll take 2 as Q. This is my Q. So 2 plus 2 is 4. So in this case I'll take R as 0. Correct? So now you can see that Q and R are unique with respect to these numbers 4 and 2, because I cannot use this Q and this R for any other two numbers. Okay, suppose if I want to use 6 and 2, and if I want to use Q and R from here, I can never use, right? Suppose if I'm using, still I'm saying no, I will use it. So what it will happen? 2 multiplied by 2 plus 0, correct? But this will never give you 6, but you want 6, you are getting 4 from here. So this makes us understand that whenever you have two positive integers, you will get two unique numbers, two unique integers. In this case, it is Q and R, where R is greater than equal to 0 and less than equal to B. That's what it is telling you here as well. Okay, so this is what we understand from Euclid's lemma. But where do we get this expression? We can also get this from regular division. Like, let me show you here. Suppose if I'm dividing 4 by 2, so 2 2s are 4, and we get remainder as 0. So from this we get the relation as dividend equals to divisor multiplied by quotient plus remainder. So this is the formula we follow. This is nothing but Euclid's lemma, where we say that quotient and remainder are unique for given dividend and divisor. Correct? In our case, dividend is 4, divisor is 2, quotient is 2. This is quotient, correct? This is quotient, and this is remainder. So remainder is 0. So from this we understand that the Euclid's lemma is nothing but this rule what we are written over here. This is used to find HCF, highest common factor. So let's understand that. To find HCF, okay, what is HCF? HCF is highest common factor, highest common factor. So generally, how do you find HCF? Suppose if I want HCF from 12 and 4, let me just write the factors for 12. How do we write? Suppose if I want to write it as 2 into 6, so 2 into 2 into 3. So these are the this is the way we write the factors, right? Like prime factors. We call it as prime factors because we know that 2 and 3 are prime numbers. So we go until we get prime numbers, correct? So in this way we get 12. And similarly, let's go for 4. What we get? 2 multiplied by 2. That's it. So what is the highest common factor? We can see that highest common factor is nothing but 4, correct? Because we get it as, we can write this as 4 multiplied by 3, here 4. So we can see that 4 is common, and this is the highest number we have in the factors. Or we can also write it as, we see the common numbers, right? We have 2 and 2, so from that we take one common, and we have again 2 and 2. From that we take one more common number. So when we multiply them we get 4. So in that way also we can say 4 is our highest common factor. So there are different ways people figure out what is a HCF. So Euclid's lemma will also help us to find the HCF. Let me see some examples to take it from. Suppose if I want HCF between say 4052 and 12576, okay, or let me take simpler number then, if it makes a mess. Well, let us start with a simple example so that we can understand, then we can go for the higher examples. Okay, uh, suppose I want HCF of 420 and 130. 420 and 130. Let me just go down a bit. Okay, so I want HCF of 420 and 130. So in general way, how do you find these factors? Highest common factor. First of all, we'll remove the factors. So for 420, I can write this as 2 into 210, and that can be written as uh, 3 into 70, and then that can be written as uh, 2 into 35. So 2 into 3 into 2 into 5 into 7. So basically we can write this as 2 into 2 into 3 into 5 into 7. So these are the factors for 420. Okay, the prime factors. What about 130? Let us find the prime factor for 130. So we can write this as 2 into 65. So 2 into 13 into 5. So we get 2 into 5 into 13. Okay, so now let us try to figure out the common numbers like 2 and 2. So we have 2 multiplied by, we don't have any more 2s, we don't have any more 3s, but we have 5. Okay, so 2 5s are 10. So we can say that 10 is the highest common factor for 420 and 130. But the question is how to use Euclid's lemma to find the HCF of 420 and 130. Okay, how to do that? We'll use Euclid's lemma, because when we divide 420 using 130, what we have to do is, let us take the first factors. We have to decide with what we have to divide, so that we'll get 420. So anyway, 420 420 is not in the not in the table of 130 to get 420. So what we'll do is we'll multiply it by 3, because 130 into 3 is 390, correct? And what we'll get is we'll get 30, correct? So we can write 420 as 130 multiplied by 3 plus 30. As we can see that 3 is quotient, and 30 is remainder. In this, what we understand is this is R, and this is R. We can say that this has A and this has B. So this is our A, this is our B, this is our Q, and this is our R. So now what we have to do is, since the remainder is not zero, we have to continue this process taking B and R. So this time B will take the position of A, okay, and R will take the position of B. So now we have to find new Q and new remainder. Okay, how can it be done? So 30 multiplied by 4 is 120 plus 10, then it gives us 130. So in this, our new A is 130, new B is 30, and new Q is 4, and new R is 10. Still you can see that R is non-zero. So you have to continue this process. Now this time, again the same process, repeating the same process. B will become new A, R will become new B, okay? And we have to find new Q and new R. So 30, 10 into 3, so 30, so remainder has to be 0. Fine, so this was our new A, and this was our new B, this is our new Q, and this is our new R. What we observe is R is 0. So when you reach this point where remainder is 0, at that point of time, you take this B as HCF. So this is how we find highest common factor, correct? I repeat, whenever you are given with two numbers, here if you see 420 and 130, and you are asked to find the HCF using Euclid's lemma, you first of all convert that into this form, basically finding Q and R, okay? That you can find by the regular division, and you write it in the form of dividend equals to divisor multiplied by quotient plus remainder. But when you see the remainder is not 0, then you proceed the same process further by taking B as new A, R as new B, and find new Q and new R. And we saw that R is not 0 even in this case. So again repeat the same process. Now this time this B will be new A again, and R will be new B again, and you have to find new Q and new R. So once you get R as 0, you fix that the B is your HCF for the given numbers. Okay, so that's how you find it. So let's solve few more questions for finding HCF. Let me just see the list of the questions I'm having. Okay, let us try to find HCF of 135 and 225. The question is to find HCF of 135 and 225. Let me just confirm 135 and 225. Yes. So let us try to find the HCF for this question. So first of all, we have to do the regular division. So what we'll get is 135 ones are 135, and on subtracting we get 90. Correct? If I'm not wrong, yes, we get 90. So from this we understand that 225 can be written as 135 multiplied by 1 plus 90. So in this case, this is our A, this is our B, this is our Q, and this is our R, correct? where q is quotient, r is remainder. So when we see that r is not 0, we consider this b as our new a and the r as new b. We have to find new q and new r. So from here also we get 90 multiplied by 1, 90 plus 45, correct? So that gives us 135. So from here we understand that this is a, this is b, this is new q and new r, and we see that r is not 0. So what we have to do is we have to take this b as our new a and r as our new b, and now we have to find new q and new r. So 45 multiplied by 2 plus 0 gives us 90, correct? So this is our a, new b, new q and new r. And what we see is r is 0. So immediately we can consider this b as HCF of 135 and 225. So 45 is the HCF for 135 and 225. We can cross check that with the regular method which we use by finding the prime factors. How we can do that? Let us just see. We are rechecking, okay, by the basic method which we have learnt in different standards, the lower standards. So 135 can be written as, how to write this, 5 multiplied by 5 2s are 10 and 7s are 35. Okay, so 5 multiplied by 3 multiplied by 3 multiplied by 3. So this is how we'll get the prime factor for 35. Okay, let us continue the process for 225. In this case we get 5 multiplied by 4 and 5. So 5 multiplied by 45 is 225. So what we are getting from here, 5 multiplied by 45 is 5 multiplied by 9. And from this 5 multiplied by 5 multiplied by 3 multiplied by 3, because 9 is 3 multiplied by 3, right? So both cases we got the prime factors. So we just have to see what are the common factors. We have 5 in common. Okay, 5. We don't have any other 5, but we have 3. We have still 10 over here. Okay, multiplied by, we have one more 3 in common, correct? Okay, then we don't have anything else as common. So whatever we are getting from here will be our HCF. So 5 multiplied by 3 multiplied by 3, which gives us 45. So you can consider, or you can check from this way also, that our HCF for 135 and 225 is 45. Got it? Let me just see one more question. 867 and 255. 867 and 255. Let's try to solve this. We have to find the factors for, find HCF for 867 and 255. 867 and 255. Before moving further, I just want to remind you that you can visit our website www.letstute.com. For a wide range of courses are there regarding mathematics and different things. You can just go through and browse through our site to check out those courses. Okay, fine, let's move further. Now in this case, let's try to, now this time let's go other way. Let's find it by the basic method and then we go for the Euclid's lemma. Okay, 867 can be written as 2 1s are, we cannot get it by 2 anyway. So I'm figuring out how we can find this. So 8 by 8, yes, we can find it by 14, yes, we can find it by 3. Okay, so let me just erase it. Let us find it by 3. So 3 multiplied by 3 2s are 6. So 26, 3 8s are 24. Yes. So 3 multiplied by 289. So we are getting this. So can we find factors for 289 further? I'm just trying to understand this. What I'm figuring out is we cannot find this. So let's keep it as it is. Let's try to figure out. I think we should get. Wait. 7 3s are 2 plus 8 7 10 10 plus 9 19. Okay, let's try to find it using 7. Am I getting it? 7 3s are 21. 79. No, we are not getting by doing that. So are we getting by 13 ones are 13, 32s are 26, 29. For timing, let's try to find the factors for 255 as well. Then we get the proper idea for this. For 255, we are going to use 5. So 5, 5s are 25, 5 ones are okay. So 5 multiplied by 3 multiplied by 17. Okay, so I think we should get it something from 17 from here. Okay, so 17 ones, yes, I think we are getting it. 17 ones are 17, and we are left with 1 9. So 17 sevens are correct. So it is 17 squared basically. Yeah, 17 squared is 289. Sometimes it's a brain fade that we don't get it. Anyway, so 17 sevens are that's 119. Yes, it is 289. Yeah, you're right. So 3 is in common. So we get HCF as 3 multiplied by 17 we have in common. So we take it as 15 is our HCF for 867 and 255. So this is by the standard method, the basic method. Let us try to find this using Euclid's lemma. Okay, so we have to divide 867 by 255 for getting the basic relation. So 255 multiplied by, let me just have a rough work over here. 255 multiplied by 3. Let me just find out what we are getting. So 3 5s are 15. 3 5s are 15 plus 1 16. 3 2s are 6 7. So let me just reconfirm. 15 3 5s are 15 16. Yes, 3 2s are 6 7. Yeah. So 255 3s are, we get 765. Okay, on subtracting we are getting 7 minus 5 it's 2, 6 minus 6 it's 0, we are getting 102. So what we understand is 867 can be written as 255 multiplied by 3 plus 102. Okay, so in this case our A is 867, B is 255, Q is 3, and R is 102. So we see that R is non-zero. So what we are going to do is this B will be our new A, and R will be our new B, and we have to find uh, new Q and new R. So let us just try to understand that it is 102 multiplied by 2. We are going to get 204 plus 204 plus 51. Yes. So we are going to get this relation. So this is a new A, this is a new B. So this is a new Q and this is a new R. R is non-zero. So we are going to use this B as A, new A, and R as new B. Correct? So new Q would be 51 multiplied by 2. We are getting 102. So remainder would be 0. So A, B, Q, and R. We see that R is 0. So we consider this B as our HCF. So HCF of 867 and 255 is 51. So this is how we conclude that even by Euclid's lemma, we are able to find the HCF. And this is pretty much useful in different problems and in different further concepts, which we are going to see in coming lectures, that Euclid's lemma is very much useful in finding different things and to find different relations between the numbers. So today we have learned different things. Let's just go through the things what we have learned today. Yes, we have seen what are natural numbers. Natural numbers which are starting from, which are existing naturally, which starts from 1 and goes further. Just we use them for counting. And then we have seen what are whole numbers. Whole numbers are basically when we count 0 along with natural numbers. The numbers which we get are called as whole numbers. And then we saw what are rational numbers. Rational numbers basically ratio of two integers. Okay, so that's what we have defined for rational numbers. That is already pre-existing definition. But the numbers which we are not getting by taking as fraction of two integers, they are called as irrational numbers. And we saw some examples, like here we saw pi, which is 3.14, etc., which cannot be written, which cannot be represented by any two integers, fraction of any two integers. So therefore they are called as irrational numbers. Like similarly we saw root 2, we saw root 3. The numbers which we are getting, they are non-repetitive, non-repeating. But we still have seen some fractions, some decimal numbers which are never ending but they are repeating. So what we understand is never ending and never repeating, both the conditions are need to be considered for irrational numbers, correct? Because we've seen some examples where they are never ending but they are repeating. So therefore they are also represented by the fraction of two integers. So even in that case they are rational numbers. So we have seen that 2.333, it is a rational number. 1.6666, it is also rational number. But in case of these numbers, these are never ending and never repeating. Therefore they are called as irrational numbers. If we move on further, we have seen some hierarchy, that we know what are rational numbers, we know what are integers. Integers are negative, positive, both. Positive numbers are also called as natural numbers. And we have irrational numbers. Just now we have understood that they are non-repeating decimal numbers, decimal digits, and never-ending decimal digits. So they are called as irrational numbers. And all these types of numbers constituting real numbers. That's what the chapter's name. Okay. And then we have, till here we have covered all types of numbers. Then we are going for Euclid's lemma. What we understood, that if we have two numbers, two positive integers, then we can find two more positive integers using this condition. We have to consider this condition, but we are going to get those two integers unique integers. Okay, so that's what we are trying to see with the example of few things. Like we have taken 4 and 2, we understood that the 2 and 0 what we got from here, that they are considered as q and r, cannot be used for any other combination. They are going to use only for this combination, correct? So therefore we see that they are always unique. Okay, it cannot be repeated for any other pair. And we have seen how to find HCF using Euclid lemma. We have seen different examples that we already had one method of finding prime factors and seeing the common, and then multiplying the common factors from both the numbers, common prime factors, to get the HCF. That is a basic one. But we also understood that how to find it using Euclid's lemma by using the relation called A equals to B plus Q. A equals to B multiplied by Q. B multiplied by Q plus R, where R is greater than equal to 0, and less than B. So this is the relation which we are trying to figure out. But what we've seen is, whenever R is not 0, we consider B as new A and R as new B, and we continue this process until we get remainder as 0. Once we get remainder as 0, from that step B is taken as HCF. So that's why we've seen some examples, some questions, and we are done with this today. So that's it for today. And I want to remind you that if you have not subscribed our channel, please subscribe. And if you're not, press the bell icon. Please press the bell icon so that you will get the further notifications, so that you may not miss any notification from our channel. And also please visit our website www.letstute.com for all diverse kind of all the courses which we have. It's a wide range of courses which you can go through. Fine. Okay, then fine. See you next time. Till then, take care.